Welcome to the video for section 4.0. This is the first and only time that we will be looking at one of the zero sections from a chapter. This is usually called the Getting Started section, and these are usually review type concepts, which we discuss but don't give their own time to, particularly. This section, however, contains some information about complex numbers which you may not have seen before, and that's why we would like to highlight this. This is one of the competencies that we're hoping you leave this class having mastered. If you consult the notes PDF on page 47, you'll see the introduction to the idea of a complex number. So we've run across this idea that you can't take the square root of a negative number, and yet from time to time mathematicians would encounter these expressions, such as the square root of negative 16, as solutions to equations. So quite a while ago, they came up with the idea of let's let a number stand for this concept. And that is where the square root of negative 1 began to be useful. So this number I is defined in the notes, definition 4.1, to be the number whose square is equal to negative 1. This implies that I itself is the positive or negative square root of negative 1. So I is a little bit shifty, but we can use it to simplify numbers like the square root of negative 16. Remember that the square root of negative 16 is just the square root of negative 1 times 16. And the square root of a product can be broken up as the product of the square roots. So we could say this is the square root of negative 1 times the square root of 16. Now the square root of 16 can be simplified to positive or negative 4. And this quantity, square root of negative 1, can be simplified as I. Now, for our purposes, we aren't actually going to need the plus or minus whenever we take the square root of a number. The result is what we call the principal square root. So this would actually be just 4, and this piece would be I, so our result would just be 4I. We describe any number involving this unit I as either complex or imaginary. This particular number, 4I, is imaginary. If you read the definition just below the definition of the imaginary unit, it says that any complex number is a number that can be written as a plus bi, where a and b are both real numbers. So something like 2 plus 3i, that would be a complex number. This number has two parts. We have the real part and the imaginary part. Now, if a complex number has only a real part, then we would say that number is real. For example, the number 2 is real. On the other hand, if the complex number has only an imaginary part, that is, if the real part is 0, then we say that the number is imaginary. In this fashion, we can see that the real numbers are contained within the complex numbers. Since every real number is technically a complex number which lacks an imaginary part. Within the complex numbers, we also have the imaginary numbers. Those are the complex numbers which lack a real part. And aside from all of that, there are infinitely many complex numbers which have both a real part and an imaginary part. On the next page, you'll see the definitions of arithmetic with complex numbers. We pretty much treat a complex number just like a binomial. We have the real part, which can be combined with other real parts of other complex numbers. And we have the imaginary part, which can be combined with other imaginary parts. So for instance, if I wanted to perform the operation and simplify, for an expression of the form, let's try 2 plus 3i plus 5i. Here we're adding a complex number and a purely imaginary number, but the way that we can do that is by adding like terms. So I have 2 plus 3i plus 5i, and I'll combine my 3 and my 5i to give me 8i, and that is our solution. That is the sum of these two imaginary numbers, or I should say complex numbers. We can do the same kind of thing with subtraction. If I have the complex number 1 minus 3i minus 1 plus 3i, let's see what we end up with. Well, I would like to distribute the negative. Remember, we're subtracting 1 and 3i. So I'll be left with 1 minus 3i from the first piece, minus 1 minus 3i from the second piece. Now my like terms, my 1 and my minus 1, will give me 0, and negative 3i and negative 3i give me negative 6i. So here we end up with our final answer, negative 6i, a purely imaginary number, from adding these two complex numbers together. So adding, subtracting, multiplying, dividing two complex numbers will always return another complex number. Now that complex number may be purely real, it may be purely imaginary, or it could be some combination of the two. So let's see another type of operation. Suppose we have 1/2 minus 9i, and we would like to multiply that by 2 plus 2i. Well, again, I'm treating these complex numbers kind of like they are binomials. So here I'm multiplying two binomials, and in the real numbers I would do that by FOILing. So I'll FOIL, and I get 1/2 times 2. Outside would give me plus 1/2 times 2i. Inside would give negative 9i times 2. And last would give us negative 9i times 2i. So my 1/2 times 2 would just leave us with 1. 1/2 times 2i would leave us with I. Negative 9i times 2 would leave us with negative 18i. And negative 9i times 2i would leave us with negative 18i squared. So we're nearly done. The last thing that I would like to do is simplify this completely, write it in that form a plus bi, so the standard form. So I have 1, my I and 18i can combine, leaving us with negative 17i. And what is going on with the I squared? Well, standard form is a plus bi. That doesn't leave any room for any I squareds. So we go back to the definition, which says that I squared equals negative 1. That's a good fact to remember. So negative 18 times negative 1 is what we're really dealing with. Alright. When we look at it in those terms, we can see we have 1 minus 17i plus 18, and there I can combine two more like terms. 1 plus 18 gives me 19, and I have negative 17i still hanging around. So there we have our standard form. It turns out the product of these two complex numbers is this new complex number. For part D here we have a similar concept. We're multiplying one complex number by another, but in this case we don't need to do as much work. We can still treat these complex numbers as if they were regular expressions. So if I multiplied 2 times a binomial, I would do that by distributing that 2 into both terms of the binomial. So 2 times 1/2 and 2 times 9i. So our simplification here is going to be a lot easier than in the previous problem. This would just give me 1 minus 18i. Now let me show you one more complex multiplication before we look at the question of division. So here in part E, we see the product of two complex numbers. Each one has a real part and an imaginary part. And I will simplify this again by foiling. So if we do the first terms, that would leave me with 9. The outside would leave me with negative 6i. The inside would leave me with positive 6i. And the last terms, 2i times negative 2i, would leave me with negative 4i squared. Now the interesting thing about this particular problem is that the negative 6 and the positive 6i cancel, and I'm left with 9 minus 4. And remember, I squared is special. We can replace that with negative 1. So we're really just talking about 9 plus 4, or 13. So one way that you can be guaranteed that when you multiply a complex number and another complex number, if you want to end up with a real number, then those complex numbers need to be what we call complex conjugates of each other. So something like a plus bi and a minus bi. These are complex conjugates. And that is always the case whenever we have the same magnitude, the same real part, and the same imaginary parts, but opposite signs in between them. So in this problem, we multiply 3 plus 2i by its complex conjugate 3 minus 2i. We can also view that as multiplying 3 minus 2i by its complex conjugate 3 plus 2i, and we end up with our result of 13, this real number. That is the strategy that we use to simplify quotients of complex numbers. So for something along the lines of 1 plus I over 1 minus 2i, we would like to write this in that standard a plus bi form. That form does not have I in the denominator. In other words, we don't want a complex number in the denominator, and so we are going to try to get rid of the complexity of this expression's denominator. Now we can do that by multiplying the denominator by its complex conjugate, 1 plus 2i. But if I go multiplying part of a fraction by something, in this case the denominator, I have to multiply the numerator as well. So notice that I am multiplying by 1, essentially. This whole expression, 1 plus 2i over 1 plus 2i, this is just a very strange way of writing the number 1, so this is equal to what we originally started with. Alright. So now I need to multiply the numerator and the denominator out. So remember, multiplying fractions, you're going to multiply numerator by numerator and denominator by denominator. So that would leave us with 1 from the first terms, plus 2i from the outside, plus another I from the inside, and I times 2i would leave us with plus 2i squared. Now our denominator, since we chose to multiply by the complex conjugate of our original denominator, will look something like this. We'll get 1 from the first term, plus 2i from the outside terms, minus 2i from the inside terms, and minus 2 times 2, 4i squared. Now, where's that going? Well, I'll try to simplify the numerator as best I can. That would leave us with 1. I can combine 2i and I to give me 3i. And 2 times I squared is 2 times negative 1. So we're making progress. The denominator will see something similar. The 2i and the negative 2i will cancel just as they did in that second to last, or last problem that we looked at. My denominator now is just going to be 1 minus 4 times negative 1. So I'm replacing all those I squareds with negative 1s. So let's do a little bit of cleanup. This is 1 plus 3i minus 2 over 1 plus 4. So finally that leaves me with 1 minus 2 negative 1 plus 3i over 5. And I want to take this one step further. I want to know what the real part is and what the imaginary part is. So I can break this up as negative 1 over 5 plus 3 over 5i. That is the standard form for that imaginary or complex number. This is not pure imaginary since we do have a real part. And that is equal to what we started with, 1 plus I over 1 minus 2i. So if I divide the numerator by the denominator, this complex number is the result. On the next page of the notes, there's a discussion of the properties of I pertaining to what happens when we raise I to certain powers. So remember that anything to the 0, except for 0 of course, is 1. Anything to the first is itself. Anything to the second doesn't have a good rule, but this number, this special number I, when we square it, we get negative 1 by definition. And if we go a little further, we can think of I cubed as I times I squared, which gives us negative I. So these are the first 4 powers of I, and this is the pattern that's going to repeat for every single power of I, or every integer power of I, from here onward. We won't have to look at anything crazy like the square root of I or anything like that. Those things do exist, but they're beyond the scope of this course. We're just going to look at whole number powers of I. So the way that this pattern repeats, every fourth power, we start over again at 1. Then we go I, negative 1, negative I, and then we'd start over again at 1. So if I wanted to find a very large power of I, all I would need to do is figure out which piece of this sequence that power corresponds to. Is it related, is it 4 away from I to the 0, I to the first, I to the second, or I to the third? And we can determine that using division. If we divide the power that we have by 4, the remainder will be one of these 4 powers, 0, 1, 2, or 3. So let's look at an example of that. So the first one that we'll look at is I to the 16th. Now it would not be impossible for us to just count out the rest of these powers of I to the 4th, starts over at 1, I to the 5th, is I to the 6th, is negative 1, I to the 7th, is negative I. Here we go, I to the 8th, starts over again at 1, then we do 9th, that would give us I, negative 1, negative I, for 10 and 11. 12 would start over again at 1, 13, I, 14, negative 1, 15, negative I, and finally the 16th power of I would be one where we start over again at 1. Well, that was quite a bit of work, and it would not be very helpful if I wanted to solve the second problem that we see here. When I have an extremely large power, such as 2096. So what I'll do instead for these types of problems is I'll take 16, I'll divide that by 4, and I'll see what the remainder is. Now we know that 16 is divisible by 4. We can fit 4 in 4 times. If we multiply those, we get 16, and subtract to get a remainder of 0. So I to the 16th is identically equal to I to the 0, which we know is 1 from those 4 important repetitions there at the beginning of this sequence. So we can do the same thing with a number like 2096. We can take 2096 and divide that by 4. Well, this is where long division is going to come in handy. I can fit 5 into 20. And I'm left with 0. If I bring down the 9, I can fit 1, 2 in there. So I'm left with 1. Bring down the 6. And we can fit 4 into 16, leaving, again, a remainder of 0. So it turns out that I to the 2096 is also equal to 1. Let's see one more of those. Here we have I to the 509th. Again, it would not be convenient for me to count out to 509 and see which of the 4 possibilities we end up with. So instead, I'll take 509 and divide that by 4. And I think we can fit 4 into 5 once, leaving a 4. Bring down the 0, and we can fit 2 4s into 10. We subtract 10, that leaves us with a 2, bring down the 9, and I think we can fit 7 4s into 29, so 28 is a multiple of 4. So we have a remainder of 1 in this case. We would say I to the 509 is equal to I to the 1st, and anything to the 1st is itself. So there we get our solution for I to the 509th. Here we've seen a bunch of positive powers of I, but what about something a little more interesting? Let's look at I to the negative first. Now in this type of problem, we're kind of playing around with both what we now know about this imaginary unit and properties of exponents. So remember, if you have a negative exponent, you can write that expression, instead of I to the negative first, we could write this as 1 over I to the first. Well, we know that that denominator is equal to I, so we have 1 over I, but that is not completely simplified. Remember, our completely simplified form would be something like a plus bi. It doesn't allow for any i's in the denominator. So I want to get rid of that I can do so by multiplying by this complex number's conjugate, which is negative I. If I do that, then we end up with negative I in the numerator and negative I squared in the denominator, which is good news for us because negative I squared is equal to negative 1. So this is just negative I over 1, or negative I. So we see that this pattern actually repeats in the other direction. The negative first power of I is negative I. If we kept going, we would see the next smallest power would be negative 1, then I, then 1. Then negative I, then negative 1, then I, then 1 again. So that pattern continues in both directions. Now, we can use this idea of the negative exponent creating a fraction to solve something like our next problem, and indeed the last in this section. So here we have something pretty exotic, I to the negative 25th. Well, the first thing I would do is say that's the same as 1 over I to the positive 25th. And then I'll do a little side work to figure out what I to the 25th is. Well, 25, when we divide it by 4, leaves me with a remainder of 1, since we can fit 6 4s in there, leaving 24. If we subtract that, we have a remainder of 1. So I to the 25th and I to the 1st are equivalent, so this is I. And here we would say, okay, 1 over I to the 25th is really just another way to say 1 over I. And we've already done the work. We know that 1 over I ended up being negative I. So this is equal to negative I. We don't have to do any more heavy lifting. Those are the techniques that we're going to use for problems out of this homework set. Go ahead and get started on those. It's a pretty short section. Bring any questions that you have to class.